Hi friends, today we are going to discuss about the potential energy of the system of charges. Okay, so first I am going to bring a positive charge from infinity to at a particular point. So I suppose to take, so this is my x, y, z coordinates, this is my 0 point, this is my origin. So if you want to bring a charge q1 from infinity to my required point, so I am just bringing this my charge q1 from infinity to the position vector r1 vector. What is my r1 vector? So my r1 vector is nothing but xi plus yj plus zk. Okay, the position vector of the first charge in the xy z coordinate. So the amount of work done required to bring this charge is going to be 0. Why it is 0? Because there is no opposition. So if according to your work energy theorem, if you are doing work against some force, or this work done stored as the energy of the system. In this case, there is no opposition. So the amount of work done bringing this charge from infinity to this point is going to be 0. So I just use this space here. So the work done to bring q1 is 0 because there is no opposition. So the next one is the potential produced by this around this. So I can measure this, since it's a positive charge or negative charge, doesn't matter. Now in this case I am considering this a positive charge. Because of this charge configuration, here we have a potential, here we have a potential, here we have a potential. At any random point we have a potential around this. So the potential produced by this q1 at any random point, in this case I am going to take it as a point P. So the potential due to q1 at point P, I can simply write potential due to first charge at point P. I can simply write 1 by 4 pi epsilon naught q1 by r1p. R1p is nothing but, if I consider this point is my P, so the distance from here to here is going to be r1p. R1 is fixed, my P is the variable. My P point may be here, 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 anywhere. So the potential due to this positive charge we are writing here. So this is my equation 1. Now I just want to bring a second charge from infinity to this point. So if I want to bring this charge from infinity to at this point, I have to do work against this repulsion, the potential produced by this charge. So this charge is going to oppose my second charge. So if you want to bring my second charge from any random point, is going to be infinity to the position vector is going to be r2 vector. This charge is going to be q2. So I have to do work against the electrostatic repulsion produced by this charge. This charge is going to oppose this charge. So I have to do work against this electrostatic repulsion. So I can simply write the work done to bring q2 from infinity against potential due to q1. So I can simply write my work done W2. Okay, this is equals to, so work done on 2. So I have to do work against this electrostatic repulsion. I can simply write my, I am going to bring my q2 against potential due to first charge at r2. So initially we took any random point P. Now I know the position vector of the second charge is r2. So this is a potential due to first charge at the position vector of the 2. So I can simply write this is nothing but, if I substitute this equation 1 there, I can simply write 1 by 4 pi epsilon naught q1 q2 by r12. So instead of taking r1p, I can just replace p by 2. Okay, this is my potential energy of the this system. So for first charge, the work done is 0. The second charge, we have to do some work. So this work done against this repulsion produced by the Q1. Now we have two charges. So this charge which will produce potential around this charge will produce potential around this. So now we have two potential. One is due to Q1 and another one is due to Q2. So I have to write the potential due to Q1 and Q2 at any random point P or here, anywhere. So I can simply write the potential due to Q1 and Q2 at any random point P. I can simply write here V1 and 2. Okay, so I can simply write 1 by 4 pi epsilon naught is going to be common out. So Q1 by R1P. So this is a, if you multiply this, what's happening? So potential due to Q1 at R1P at point P, and then I can simply write my Q2 by R2P. P is any random point. I am telling you this point may be here. The distance from here to this will be R1P. The distance from here to this will be R2P. So now we have a potential. This is my equation 3. So if I just want to bring the third charge from infinity to the required point Q3, the distance from here to this will be R3 vector. So I have to do work against this potential as well as this potential. So this charge is going to repel this charge also is going to be repel this charge. So I have to do work against both the charges. So I can simply write the work done on Q3 against potential due to Q1 and Q2. So I can simply write my W3 equals to, actually W1 is 0, right? W3 equals to Q3, I am going to work against 1, 2, okay? So I should not use this 2 in here, okay? So potential due to 1, 2, right? So if I substitute this here, 1, 2 here, equation 3 here, then I may write 1 by 4 pi epsilon naught Q1 Q2 sorry Q1 Q3 by R13 plus R13 means the position, the distance from here to this will be R13, the distance from here to this will be R23, right? So the distance from here to this will be R12, clear? So I may write here Q2 Q3 by R23. So this is my equation 4. So this is the amount of work done required to bring my third charge. The next one is how can we calculate the total potential of this system. So we are going to add my equation. Actually work done by the first charge is 0. So I am going to add my 2 and 4. So the total work done is nothing but my, I may write my equation 3, 2 and 4 here. My total work done is nothing but my total potential energy of this system equals to 1 by 4 pi epsilon naught Q1 Q2 by R12 Q1 Q3 by R13 plus Q2 Q3 by R23, right? So this is the total potential energy of this system of charges. So in this case, the beauty of this equation is my final expression which is independent of the path. So that's why it's called conservative force. What is meant by conservative force? Conservative means this path independent. So it's purely depending upon your final position of the particle. First you are bringing first charge or second charge or third charge, it doesn't matter. So I need only the position vector, I need only the magnitude, okay? I should know the final position of the particle, the entire system, how it is assembled. Okay, so my electrostatic force is the conservative force. Conservative force means it's a path independent force, right? It's a path independent. So I may bring my second charge here, for the third charge here. So I have to do work against the electrostatic repulsion. See, for example, if I have my bowl, if I bring my first charge, the work done is 0. If I bring my second charge, I have to do work against the first charge. If I have a bowl with 10 charges, if you want to bring my 11 charges, means I have to do work against the 10 charges repulsion. Okay, listen carefully. Again, I am telling you, electrostatic force is a conservative force. Conservative means it's a path independent. So I need only the final position of the particle to find the electrostatic potential energy of the system. Okay, so I'll give an example here. So after this, I'll give an example here. First, I'm going to start with, I'm going to consider listen carefully. In the exam point of view, in the CBSE as well as the competitive exam point of view, they are asking you to, what is the amount of energy to associate a particular charge configuration. So you need to write these steps. In the case of theory question, you have to derive this entire thing. But in the case of problems or competitive exams, so don't do this completely. You just write the final configuration and the initial configuration, the energy difference between these two. Simple logic. So I am supposed to consider a charge Q1 here. Okay, charge Q2 here, charge Q3 here. This is my position vector R12, R23, R13 vector. So what is the amount of work done required to associate this charge configuration? In case suppose to take, this is going to be 1, this is going to be 2 coulomb, this is going to be 3 coulomb. Okay, so I may write the amount of energy required to associate this charge configuration. I can simply write my total potential energy I can simply write U equals to 1 by 4 pi epsilon naught Q1 Q2 by R12 plus Q2 Q3 by R23 Q3 Q1 by R31 or 13 doesn't matter, this is a magnitude, right? So this is my potential energy of this final configuration. If I know my Q value, if I know my R value, I can find the U final, because initially this charges from infinity. So the potential energy at infinity is going to be initial means at infinity is going to be 0. The potential energy at infinity is going to be 0 because R is going to be infinity, means my potential energy is going to be 0. So the final potential energy is nothing but, so the work done is nothing but the difference in the potential energy. My W equals to U initial minus U final minus U initial. Anyway, this is going to be 0. I can simply write whatever the value I am getting here. Say for example, after substituting my R1 equal to 1, this is going to be 1 meter, this is going to be 1 meter. So if I simplifying this, if I get, this is going to be some 5 joules. So this is going to be 5 joules. This is the work done required to assemble this charge configuration, right? Sometimes they are asking you to find the amount of work done required to disassociate this charge configuration. How can we dissociate this charge configuration? Simple logic. Now this is going to be initial, this is going to be your final, your work done will become negative. That's it. Just interchange your initial and final position. So this kind of questions they are asking in the 2 marks probably. Okay. So in the case of NEET exam or JEE exam, they will ask this kind of questions. So the amount of work done required to associate this charge configuration, and then the amount of work done required to dissociate this charge configuration, they may ask these questions, right? So next I'll teach you what's happening when the external electric field is applied. Okay, so the next concept is potential energy in an external electric field. We have a potential energy in an external field. Okay, so we have a electric field in this direction, which means we have positive charge here, right? So I just want to bring a positive charge from infinity to my required point. In the previous case, the work done on the first charge is going to be 0. But in the case of external electric field, if you want to bring a positive charge from infinity to this point, I have to do work against the external field. So if you want to bring this charge q1 from infinity to this point, I have to do work against the external electric field. So the potential due to this at this point, I can simply take the V. So the work done to bring q1 against external field, am I right? This is going to be q1 potential due to external electric field at point r1. This is my equation 1. So in the previous case, my work done against work done to bring my q1 from infinity to at this point is going to be 0. In this case, is going to be a non-zero value because we have to do work. There is a external electric field. We have to do work against this external electric field. So this is nothing but my potential at point r1 due to the external electric field. So next, if you want to bring the second charge q2 from infinity to this point, first I have to work against this potential and as well as the potential due to this charge. So this is my position vector r2. The distance from here to this will be r12. Then am I right? The work done to bring work done on q2 against external field equals to q2 V of r2, which means the potential due to external electric field at the position of r2. It's a function, right? So next, this will produce some potential around this. Next is the potential due to this. I have to work against my q1. So the work done on q2 against potential due to q1, then am I right, is going to be 1 by 4 pi epsilon naught q1 q2 by r12. So the separation from here to here will be r21. So r12. So next, the total potential energy of this system of charges. So the total energy, actually this is the potential energy in an external field of system of 2 charges. So in the syllabus we have only up to 2 charges. So total potential energy of system of charges, of system of 2 charges in an external electric field, we write U is equal to q1 V is a function of r1, q2 V is the function of r2 plus 1 by 4 pi epsilon naught q1 q2 by r12. So this is the potential due to the external electric field. This is the work done against the external electric field to bring my first charge. This is the work done to bring my second charge against the external electric field. This is the work done to bring my second charge against the potential due to the first charge. So this is the total potential energy of the system of 2 charges in an external electric field. So this is very important concept for the 2 mark question in the CBSE exams as well as for your NEET and JEE exams. Okay, so I just stop at this point. So if you like this video, share with your friends and subscribe our channel to get the more content. We'll meet in the next video. Thanks for watching.